welcome again. Today we're going to take a look at interactions. Up to now we've been discussing a very special quantum field theory called the Klein-Gordon quantum field. We've introduced a Hilbert space and a Hamiltonian to describe the dynamics of what we now know to be a relativistic quantum field called the Klein-Gordon quantum field, phi hat at Tx. And we also know that this obeys the Schrödinger equation. I think there's a plus there, right? Yeah, there's a plus there. This field evolves according to the Schrödinger equation, and in the Heisenberg picture it looks like this, and HKG is the generator of time translations. And also, in the previous lecture, we quantized the Poincaré group for this model by discovering a representation of the Poincaré group in terms of field operators. We did this in the previous lecture. We discovered a quantization, which is to say we've really furnished a unitary representation of the Poincaré group in terms of these field operators here and the Hamiltonian of the field, the Klein-Gordon Hamiltonian. So it's in this particular sense that we have constructed a relativistic quantum field theory. We found a space of states and a representation of the full Poincaré group on that space of states in terms of these field operators, and hence we are basically done. We could spend a long time studying the dynamics of this theory. How does it evolve? What happens if you hit it here? What happened over there? And people still study this theory to this day in ever more Baroque setups. And the reason they do is because it's so very nice. This is an example of a free theory. And the thing about free theories is you can easily solve them and say what happens for all time after you've solved the free theory. So that's good. I'll say I think we can say that fairly confidently. Almost all free theories that are interesting are easy to solve. But they are free. And free means that there's no interactions. If you construct a particle by hitting the field or making it interact with a short time with some reservoir, and you bring a particle into existence and allow it to evolve, so here's like a space-time picture. Here's time, here's, oops, other way around. Here's time, here's space. Imagine that there's an event which creates a particle at some time, at the origin, say time t equals 0. The particle evolves according to the Klein-Gordon Hamiltonian, so it somehow propagates out. Suppose there's another particle that's created over here, and it also commences some propagation. Well, the thing about theories such as this is the presence of other particles does not affect the dynamics of one particle. The particles just evolve completely independently of each other. And that's easy to see because if you look at the Hilbert space just of two particles, so the Hilbert space of two particles is spanned by states like this. And how does a state like, well, I've got to now commit to actually putting some kind of momentum distribution on these two particles. So we'll do that now. So we have some two-particle state like this, and then you might wonder, yep.
Shouldn't there be a dagger at the AQ?
Shouldn't there be a dagger at the AQ? Yes, thank you very much. There should be a dagger at the AQ. This is a two-particle state. You create a particle with highly localized momentum at Q and one highly localized momentum at P, and then you smear them out by some distribution function in momentum space. This subscript here is meant to mean localized at x. Any such two-particle state is some linear combination of these things. And then you might wonder, how does such a state evolve in time? We'll call this phi. We'll just call this quantum state phi 2. Now, how is it going to change in time? And the answer is, well, according to the Hamiltonian, right? So in some reference frame at some initial time t naught. And then if we stay in that reference frame and then wait a little longer, then this is just the solution to the Klein-Gordon equation, just the Schrödinger equation. And substituting in these fields, this two field operators AP and AQ, we are able to predict the dynamics of this state. It's just e to the minus I h kg t AP Okay, yeah, another question?
Shouldn't there be a T in the first line of the right-hand board in the
Oh yes, there should be a T up there as well, thank you. Any other mistakes? Let's see, daggers are missing, of course. Okay, it's in order. Then how does this evolve in time? Well, the thing is, the Hamiltonian is quadratic, right? Which means that this expression here is linear in the AP daggers. And these A's commute with each other. So whether or not there's another A plays no role in this calculation. So they don't interact. If you pick two localized particles of the Klein-Gordon field, you give them some initial momentum, allow them to fly past each other, then they'll do just that. They will fly straight past each other. The final state of these two particles will be independent of the initial states of all the other particles. So that's, well, so what we've constructed here is a very lovely but unphysical system. You can say everything you can about it, but it doesn't have a hope of modeling nature because nothing actually interacts with anything else. And in nature, we're pretty sure that things are interacting with other things. And so now our goal is to somehow introduce interactions into this story. And the way we want to introduce our interactions is locally. So I'll move the boards again. So we have some goals in introducing our interactions. We want to model nature. That's, I think, should be goal number one. So let me even make that clear that it's goal number one. And somewhat subordinate to this, but very, very important, is we want to maintain Lorentz invariance so that we have some kind of relativistic quantum theory after we add interactions. I mean, in some sense, that's just a subset of this requirement here because we believe nature to be Lorentz invariant. So whatever interactions we add had also better be Lorentz invariant. Now, it's sort of conceivable that there's an uncountable nightmare infinity of possible interactions out there that we should take account of. And it's basically impossible to disprove the hypothesis that you need non-local interactions. But it turns out that we can deal with 1 and 2 by positing that interactions are local. I mean, that's a principle, that the interactions should be local. You can't prove that interactions in nature are local. It might be that we're evolving according to some horrendously non-local Hamiltonian that just happens to be very well approximated by the dynamics of a local Hamiltonian. You can't ever you can't ever reject the hypothesis that we're evolving according to a non-local Hamiltonian. We're stuck with that. But it turns out that if we posit this as a principle, then we can do 2 things at once. We can still apparently model nature very well, and it makes it easier for us to maintain Lorentz invariance. So when you have local interactions, it's much easier to argue that the dynamics evolves and preserves and gives you Lorentz invariance. Now, much later on, much later on, I guess not even in this course, we'll learn, or you'll learn, depending on where you go, that this space of interactions that really matter for modeling nature are highly constrained by the requirement that they be renormalizable. So I won't be able to say very much about that in this course, but this is a very powerful argument that allows us to, with confidence, cut down the space of interactions that we need to study. But for this course, you just have to accept that there's this requirement of renormalizability. I'll argue why this is a perfectly natural constraint to put on an interaction, but only in a later course. I'm not sure we'll get to it in this course. So simply putting these 3 things together, you're motivated to study models which have Lagrangians or Lagrange densities that have a very specific form. So So the models we're going to study in this course have this particular form there. And you might be a little bit puzzled by this infinite series here. But just think about Taylor series. So this is I didn't put the arguments in here, but this is a Lagrange density, so you should be able to silently put in x dependence on all these terms like this. So classical field models that look like this is like a Taylor series approximation to some general function of phi, right? So it's a Taylor approximation to a Lagrangian of the form right? If you just Taylor expand v phi, and it should be a minus, not a plus. Then you'll write down a series that looks very similar to this. Now, the beauty of a Lagrange density like this is it's manifestly Lorentz invariant. If you do a Lorentz transformation, you can see that this term is invariant. It gets multiplied by the Lorentz transformation and its inverse here, so it remains invariant. And, of course, scalars transform like scalars, so it's also invariant. So we immediately by positing that interactions are local, meaning happening at the same space-time location here, we immediately get Lorentz invariance. So these two combine together to be a very powerful way to restrict our interactions. It'll turn out later in this, when you learn more about quantum field theory, you can constrain the sum to go from 3 to 4. The other infinite terms there won't matter. They'll be irrelevant for any physics that we can observe. And you'll further be able to throw out the cubic term because it'll make the system unstable. So it turns out there's in fact only one interacting scalar field theory. And it has the following Lagrange density. And this is the one we'll focus on later in the course. So this one and only one interacting scalar field theory is called phi-4 theory for the reason that there's a phi to the power 4 at the end of it. We will spend a lot of time talking about the quantum version of this, but only later in the course. Before we go to that, I want to talk about how to deal with interactions in general. So the fantastic thing about this model, I'll write RG. So this arrow here, why do we go from here to here? Was an argument to do with something called the renormalization group and an argument to do with stability. If you have a cubic term, then the system won't have a stable ground state. It will just disintegrate. So if you add those two together, you end up with this sort of one and only interacting quantum field theory. So we want to talk about the quantum version of this thing here. But before we can talk about the quantum version of this thing, we're going to have to agree how we're going to deal with interactions. So how are we going to deal with interactions? I know of roughly, let's say, 4 ways to deal with interactions in quantum mechanics. First way to deal with interactions in quantum mechanics and indeed in classical dynamics is by perturbation theory. You identify a small parameter such that when that parameter is 0, you can solve the system and you can expand in order by order in terms of that parameter. This is a fantastic approach to solving things because it's completely automatic. There's really no thinking that's required to carry out perturbation theory, just a lot of, let's say, stamina to keep going on with the Taylor series. The second relatively general purpose way to deal with interactions is via the variational method. In the variational method, you take a class of states that you feel on the basis of intuition or otherwise should model the system well, and you minimize some parameter, some error parameter, so that it does as good a job as it can. There's another way, which is not perturbation theory and is not variational method, and that's called Monte Carlo sampling, you somehow rewrite the problem in such a way that it's equivalent to sampling from a probability distribution. And it's not really an analytic approach in the sense that you can't do a lot of samples analytically easily, but it is arguably not really a numerical approach either. It's a probabilistic approach to the problem. And there's a fourth way, which is strictly reserved for geniuses, and that is exact solution. So you can always use that method. If you find that that's a successful and useful method for you, then I invite you to use the method of exact solution. I don't find it to be very helpful in practice. Now, in this course, we're going to focus almost exclusively on the first way, but I should say some words about the other methods, because all four of these methods have had a role to play in explaining quantum field theory. So perturbation theory has been so successful in quantum field theory that for many years, just about no other method was employed to study quantum fields. Because just about every experiment we could carry out could be modeled in some way by a perturbative argument. We'll get into that later, because we got lucky. Many of the constants of nature are actually small. So that's by far one of the most dominant methods in quantum field theory to study the solution of interacting fields. You've no doubt heard of Feynman diagrams. You will hear about them in this course. That's a systematized way of dealing with this perturbation theory approach. The variational method has not found general applicability in relativistic quantum field theory. As an approach to solving interacting relativistic fields, it's had many problems, and it's just not had any particular great successes that make it worth investigating too deeply, although that's changing as time passes. Monte Carlo sampling is arguably the only way we have of solving the equations of nature that we have at the moment. So recently, the standard model, which you'll also hear about in this course or the coming course, the standard model, which models all the interactions of the fundamental particles apart from gravity that we know of, has been numerically solved via Monte Carlo sampling to reproduce the spectrum of hadrons relatively well from a couple of given coupling constants. So this is really, I guess, the triumph of physics, is that we have Monte Carlo sampling and that we could deploy it to actually make theoretical predictions for the masses of particles that match up with the experimental results. So that's what convinces us that we have written down the correct equations of nature. And for exact solution, there are actually quite a lot of exact solutions, and they've been very useful in understanding interacting quantum fields. There's a plethora of exact solutions in 1+1 dimensions. Mostly to do with the beta ansatz, but also to do with other approaches that somehow only work in 1+1 dimensions. In 2+1 dimensions, we have topological quantum field theories. So these are the classes of field theories where you can exactly solve them because they have so many symmetries that there's just about no degrees of freedom left. So we solved those pretty well in 2+1 dimensions. And in higher, there are supersymmetric models that you can exactly solve after a fashion, from which you can learn very much. They may not be directly physically related because they might have gapless particles when you expect gapped and so on, but they are definitely tell us a lot about the dynamics of interacting quantum fields. And there's the so-called other methods like the large N limit, where you take another presumably unphysical limit, but then you end up with a theory that you could basically exactly solve. So you've got to take the word exact with a grain of salt in some of these examples, but these are the kinds of approaches that people have used to develop non-perturbative approaches to studying interacting quantum fields. Now, each of these would be several courses by themselves. So just to study variational method as a course, Monte Carlo is a course, and there's at least 4 other courses there. So sadly, we'll have to leave this discussion of interacting quantum fields and start right at. We'll start with the simplest, dumbest method you could employ when you're faced with an interacting quantum field, which is to say perturbation theory. And until you know that, there's no point in learning all these other approaches, because it might be that perturbation theory already gives you results that are so good that you'll never see the difference between a perturbative calculation and an exact solution. Because we're talking 16 decimal places here. There are many other kinds of topological quantum field theories in other dimensions. I just mentioned 2+1 particularly here. Okay, the following discussion for the rest of today's lecture will be completely general. It applies to relativistic, non-relativistic, whatever quantum mechanical system that you have in front of you. Fields, not fields. Everything I say is so completely general purpose that any quantum system you encounter from now on with an interaction term, you'll be able to use what I'm saying to solve it, or at least approximately. So we suppose that the Hamiltonian for our system has the following form. We suppose that it's a sum of two terms. And we're going to call the first term the easy term. And we're going to call the second term the hard term, or the interaction. We're going to assume we know how to calculate e to the minus I h naught t. That's what I mean by easy. It's so easy we can actually work out the full propagator. And we're also going to assume that h int is small. It's this line here, assumption number 2, that in quantum field theory things become non-rigorous. I mean, up to now, everything that we've described, everything we've discussed, everything we've written down had a way to be made rigorous. So everything in free quantum fields can be made rigorous in multitudes of ways, and people have spent vast amounts of effort doing that in more and more generality. But the minute you add interactions in quantum field theory, you have to say goodbye to rigor. There's no way to continue if you want to be mathematically rigorous. So I'll explain why quantum field perturbation theory is not rigorous and why the normal perturbation theory is. Technically, all the error estimates that govern how much error we make in these expansions are dominated by a number, and that number is the norm of that operator there, the infinity norm, largest eigenvalue. Now it turns out for interacting quantum fields, you can do a quick calculation of what that number is. Does anyone know? No matter how small lambda is, does anyone know what the norm of h int is for a quantum field? No guesses? H bar is a good guess. That's a constant of nature. but that's pretty small. The answer is infinity. For interacting quantum fields, h int is infinity. It might be h bar multiplied by infinity, but sadly, h bar multiplied by infinity, well, the infinity wins, it's still infinity. So for perturbation theory to ever have a chance of working, you actually need the norm of that interaction term is smaller than 1, and not like a teeny bit smaller than 1, quite a bit smaller than 1. And infinity is not smaller than 1. So that's why perturbation theory for quantum fields doesn't technically work, because all the error estimates we make will be errors of order infinity. That doesn't mean that it doesn't work, and that's the very peculiar thing about perturbation theory and quantum field theory, is that even though formally we require that estimate to be true, actually if you just pretend that it's true and keep writing down Taylor series, then you get answers that work extremely well. So it's worth bearing in mind that the technical estimates are a worst case estimate, as though some adversary had chosen h int. Some nasty person who wanted to make you unhappy chose your h int. That's what this estimate is assuming. But luckily nature is apparently not nasty or malevolent and has chosen h ints that have so much more structure in them that our perturbation theory arguments work even though the number here is infinity. So technically we demand that. But for this course, we're just going to pretend that it is true, even though it is not. The goal in perturbation theory and quantum mechanics is exactly the same as the goal of quantum mechanics. We want to integrate the Schrödinger equation. We want to find out what the thing is going to do sometime in the future, given that we set it up in some initial state. And it's this goal that we're going to spend the rest of this lecture solving. And a very useful way to get started on this goal is to go to something called the interaction picture, which you've probably heard of before. But I'll remind you of that now. The interaction picture of quantum mechanics is just a reference frame, changing to a reference frame, which is the change of reference frames. But you do it in such a way as to use up as much information as you know already as possible, and the information that you know already is how to integrate the Schrödinger equation for the free theory. So you want to like throw out that and just be left with the hard stuff at the end. It's the goal of the interaction picture. So in the interaction picture we define the time evolution of quantum states according to this prescription. We take the solution to the Schrödinger equation and we evolve backwards in time according to the free Hamiltonian. So you like try and undo as much of the free evolution as possible. and operators in the interaction picture, observables, because you're in a rotating reference frame, they also evolve. But they don't evolve according to the Heisenberg picture, but rather according to the Heisenberg picture just due to the free evolution. So it's just a change of reference frame. It's like instead of being stationary, you're walking relative to the system that you want to study, and your motion is determined by the free solution. So the really lovely thing about this interaction picture is that the Schrödinger equation for states in the interaction picture is a lot simpler. It's somehow simpler. I mean, of course it's identical, so it's just a change of reference frame, but it's psychologically simpler to deal with. So let's work out how does this state in the interaction picture evolve as time passes? Well, it's simple, right? You differentiate that, and then I differentiate that. So when I apply this I dt onto this exponential here, I pull down a minus h naught. And when I use the Leibniz rule and apply the differential operator to psi of t, we get the full Hamiltonian coming down. And the full Hamiltonian is comprised of the free bit, the easy bit, and the interacting bit. So that's why we do it. It gets rid of this easy term. So we're left just to focus on the hard term. But, of course, we're free to add in the identity in here. This is the Schrödinger, sorry. I should. I already had Schrödinger up there. Okay. So we add in the identity here, and then the next line, super simple, but slightly ugly notation. There we go. So that's the Schrödinger equation in the interaction picture. It's like the system evolves only according to the interaction term, but beware. The interaction term is time dependent now. So you've thrown out the easy bit and you're left just with the hard bit, but the hard bit got harder. But it's small. So remember, we assumed that h in is small. So if you look at equation star, it's formally equivalent to a time-dependent Schrödinger equation, just a time-dependent problem in quantum mechanics, right? If you forgot this subscript I here, because you were lazy, you forgot to write it down, and you wrote down this equation, and you showed it to someone else, they would say, yeah, that's just a time-dependent, that's a problem in ordinary quantum mechanics where the Hamiltonian is time-dependent. So you might wonder, how do you solve that? Well, that's what we're going to do now. we're going to be able to write down the solution to this equation by introducing a propagator type approach. It's exactly the same way you'd solve the normal time independent, the normal time dependent Schrödinger equation, but with a time independent Hamiltonian. I'm going to write the solution as some operator times by a vector. You can always do this, right? Because this is still a linear equation. And this thing here is called the propagator. Which is to be, unfortunately, easy to confuse with Feynman propagator, which isn't quite this thing. Now, you'd agree, I think, that you can solve this equation here if the propagator satisfies the following equation. So T naught is some initial time. So I think you'd agree that's a solution to that if U is a solution to this equation here. If you just substitute that equation into that line there, then you immediately write out equation star. So let's try and solve for U. Well, there's one fantastic, never-fail way to do that. Whenever you see a derivative, you integrate it. This really works. Sorry. Integrate both sides with respect to t. That will give you a solution, I promise you. Oh, I'm forgetting something. That is the solution. So can we agree to drop the I from now on? So whenever you see H in, depending on time, that really means H in the interaction picture. So this looks suspiciously easy, right? Just integrate it. So you've solved everything, haven't you? Well, indeed, you've solved the equation. This really is a solution. But it's an implicit solution. So the solution, you can only evaluate it if you find a U that's invariant under the operation of multiplying on the left by H in, integrating with respect to T prime, subtracting it from the identity, and getting U again. So the solution is expressed in terms of itself. It's a constraint. And what I'm going to do is put this seemingly tautological statement to use. So let's imagine how you might deal with this solution here. So we know that any solution to the Schrödinger equation in the interaction picture has to have this form. So one way you could go is you could just like guess a solution. Like let's stick in some matrix U. Put it in here, you put it in here, you do the integral, and you find that the left-hand side does not equal the right-hand side. Ah, okay, first guess failed. That's the first thing you might do when encountering an equation like this. And if you sort of didn't feel like pursuing it any longer, then you might give up there. But you might, if you look at that equation there and realize that it's a constraint, you might say, okay, my first guess was very bad. How about I improve my guess a bit by adding on something in such a way as to minimize the difference between the left-hand side and the right-hand side? And try again. And then you do it again and again and again, and you iteratively improve your guess until it becomes a solution to the problem. And that is the fundamental basis of what's called fixed point iteration. You make a guess, you find out how wrong you were, and then you try and minimize the error by substituting it back into the equation. We'll see how it works in the case of this example. It's very, very simple. The whole idea behind fixed point iteration is you take the left-hand side and you insert it into the right-hand side. So let's do that. Well, here's the left-hand side. Or if you like, maybe this is actually sort of closer to what we're about to do. You actually really, in some sense, substitute the right-hand side into the right-hand side. So this is a true statement. What else is a true statement? Well, if I took everywhere I saw a ut of t naught, I substituted this whole integral, then it'd also be a true statement. Okay. What I've done here is I've taken the right-hand side and I've put it into the right-hand side. Absolutely a true statement, right? If star star is true, then so is that. Well, what's stopping you doing it again? Nothing, in principle, is stopping you from again taking star star, the right-hand side of star star, and putting it into here, into the right-hand side of this equation here. Nothing stops you from doing that. You can do it again and again and again and again. Now, this is true whether or not h int is small, big, or in between. Nothing here depends on the size of h int, but the next line does depend on the size of h int. Okay, my patience is going to run out by the third order, but your mileage may vary. I think you can see how the series goes. It goes on forever, and it's comprised of terms with successively more integrals and successively more h ints. And you can prove that the nth term in this series has the following structure. Let's call this the 0th term. I think it's n minus 1. Yep. So all the terms in the series have this particular structure here with a minus I to the power n. Yeah. It's called the Dyson series. Amongst other things. And it has, this is actually a perfectly explicit and useful way to write out the series. But there's another way that we prefer to use, because as you can see, it's a real pain, right? You don't want to write this series out. You want a compact way to specify this series. And it turns out that there is another way to write it, which is somehow more easy to keep in one's mind. But before that, I just wanted to look at the norm of nth term. So if you take the norm of this nth term here, then you can upper bound it. There's a nice bound on how big it gets, right? So this integral here is the volume of the n-dimensional, n minus 1 dimensional simplex, which you can work out. It's less than t to the n, or t minus t naught, sorry, to the n over n factorial. So you can just straight out apply some triangle inequalities and some product inequalities to this to estimate this integral here, and you find that it's proportional, or it's less than t minus t naught to the power n over n factorial times by the sort of the max norm of h int over, and I'll put a star up here, over the interval t naught to t, to the power n. So this star norm is what you get when you take the supremum over the interval t to t naught of just h int evolved according to t. Of course, if this norm is unitarily invariant and h int of t is after all just h int but rotated by a unitary, so it's in fact equal to h int in the Schrödinger picture. So what you learn from this discussion is that this series is not only easy to specify every term, right, you could write them all out, there's a nice little algorithm, but they get smaller. So if h int, if the norm of h int is less than 1, then the radius of convergence of the series is like not 0. Because that's the Taylor series for an exponential. So we have an upper bound on the size of these terms. It's fantastic, right? You know, when you see a tool like this, then you just look for rocks to hit with it. And you know, we're still using it to this day. It's great. Unfortunately, this argument, of course, doesn't work for quantum fields, where this number is strictly infinity, so there we're cooked. Nonetheless, we're going to apply it as though it does work. Now there's a theorem that this Taylor series here can be re-expressed as a time-ordered exponential and this is arguably a much nicer notation than this over here. Okay, so there's this time ordering operator. And the proof is an exercise. Or is it? Is it not? Is it? It's like one line. It's super. You know, the super simplest way to prove this theorem is to differentiate the left side and to differentiate the right-hand side. And it's just one line. I mean, but I don't want you to use that proof. I want you to actually do the other proof, which is super tedious, which is to write out the Taylor series for this thing in here, bring in the time ordering operator, and then see that you get the same series there. And why do I want you to do that? It's because when the norm of this thing here is infinite, it's highly questionable whether or not that's differentiable. But you could make sense of this as generating a series. So the proof is exercise, let's say. I actually very much dislike this result because it suggests results that are not true. So it's a very fancy notation for lots of hard work. So you might think, oh yeah, great, now I know how to integrate this equation, I'll just write that down as the answer. But evaluating that thing is a nightmare. You have to express that as a series or as a path integral if you know those things. So this notation is extremely deceptive. It makes you think that the solution's easy, but it's definitely not. Proof is an exercise. It's written in any textbook you want, so I don't think you'll have troubles finding a reference for that exercise. But do it. I mean, do really write out the Taylor series for the right-hand side. All right, in the last couple of minutes, last 20 minutes or so, I want to focus on some certain observables in quantum field theory. Now, the observables of quantum field theory, well, there's lots of them. It's anything you can build out of the field operator that's self-adjoint. But we can't measure all of those infinity of observables. We focus on quantities arising from scattering experiments. Now, I discussed scattering theory in the advanced quantum theory course last semester. You can see the video. It was the last 4 videos, I think, roughly speaking, maybe last 6 videos of the advanced quantum theory course. So if you want a reminder of scattering theory, then do check out those videos again. And in that, we learned that scattering quantities are derived from things called Green's functions, and they're the quantities that determine scattering cross-sections in experiments where you hit particles against each other. Now, that's the primary means we have of testing relativistic quantum fields, is we take excitations of the field, which are particles, we make them very fast, and then we hit them against each other, and then we see what comes out. And if you recall, the S matrix is what tells us, the S matrix is what tells us about how the initial states get converted to the final states. And if you remember from last semester, you recall that the S matrix is determined by things called Green's functions, and those Green's functions, in the context of quantum field theory, have the following form. So omega here is now the full ground state of the system, and these phi 1 through to phi nh's, what are these things? Well, that's the Heisenberg picture value of the field operator at the jth field operator. What I want to do is argue how we can calculate these Green functions using perturbation theory. That's the objective now for the rest of the lecture, and maybe we make it. Once you've determined these Green's functions, these endpoint correlations, these out of time order, or these out of these non-equal time correlation functions, then you are actually able to predict the results of scattering experiments. So it's certainly not the case that this is all observables in quantum field theory, or is it? I mean, I think that's a point of debate. It's quite easy to write down observables that don't have that can't be inferred from objects like this. Just take the exponential of the sum of a bunch of quantum fields. That's a self-adjoint operator in some cases, and it is not, you can't estimate its expectation value from guys like this, but these guys certainly determine the results of scattering experiments. So it's worthwhile to focus on them. In fact, there's one definition of mathematically rigorous quantum field theory which says it's these and only these objects that we predict in quantum field theory. And a quantum field is a thing that gives numbers to these quantities. That's what quantum field theory is. It's one actual definition. That definition hasn't been met with so much success, unfortunately. Now, the claim I want to prove today is how we can predict or calculate these quantities using perturbation theory. So at the moment, it's not quite right there because this is in the Heisenberg picture. These guys. And to do perturbation theory, we had this interaction picture result, right? Well, the claim that I want to prove today is that this endpoint correlation function here is exactly equal to the same story, but in the interaction picture, where we have this mysterious S thing. Minus or plus? Ah, of course. Okay. Oh, plus minus infinity. So this is, well, it looks very much like an S matrix, this U. That's why it's called S. So that's the claim. This thing equals this thing. And, more importantly, zero is the ground state of the free Hamiltonian. So this ground state of the full Hamiltonian, that's a complete nightmare. You don't want to work with that thing. It's full of entanglement. Horrible. But this naught here, this is super nice. We know everything about it. And the proof is super easy. So you just put everything in time order. I mean, this time ordering thing is just bookkeeping. So just assume everything's in the right order anyway. And then the right-hand side numerator then becomes, I will be slightly naughty with notation. So the numerator of the right-hand side evaluates to something pretty easy. Because everything's in time order, you can just do that part of the propagator up to the time of the first insertion, do some more propagator up to the second one, and so on. Super. But that is just the left-hand side up to one extra term. Sorry. So minus infinity. And the reason that is equal to this, I mean, I don't expect that to pop out at you. It's because the Heisenberg version of an operator is equal to the interaction version of an operator multiplied by this propagator. That's something you can prove. And T naught is exactly this initial time that you choose to make the two pictures equal. So we're left with dealing, I mean, it's almost right, yeah? It's almost right. This right-hand side here looks very much like the left-hand side. But we've got this U infinity T naught on the vacuum thing. So let's deal with it. So that is equal to e to the minus, I'll do it with a limit, I guess. So this u is nothing but e to the I h naught t times by e to the I h t. And so this goes away because h naught on the vacuum is 0. This goes away because t goes to t naught. And then we're going to write things out in the eigenbasis of H. So we assume so the next line, I'm just writing out this in the eigenbasis of H. Thank you. The limit does need to be t minus infinity. Thanks. Well, it doesn't matter. What I'm about to do will show that it doesn't care. So actually, quantum field theories have continuous spectra. So here, this makes it look like there's a discrete set of eigenvalues, right? But actually, quantum fields have continuous spectra. So this sum n greater than naught is really more like dE. But this is fantastic because it allows us to deploy something called the Riemann-Lebesgue lemma. So if we consider this part of the right-hand side, and we just, for some arbitrary phi, and we let t prime go to minus infinity, then this actually tends to 0. Remember, Riemann-Lebesgue says that the limit of x tends to infinity of an expression is 0 for sufficiently nice psi of x. Wrong way around, that's okay. And how can you remember the Riemann-Lebesgue lemma? Well, just imagine you could take the Fourier transform of this. So the Fourier this is just the Fourier transform of psi, so it's psi of k. And you're just looking at the Fourier coefficient for infinite momenta. And as long as this is sufficiently nice, that's always tending to 0. It's L2. So, I mean, to actually deploy the Riemann-Lebesgue lemma, we need that this expression here is sufficiently nice. And of course, we're going to assume things are nice in this course. And so we learn that this whole term here is just 0. So the numerator equals 0 omega, omega 0, 0, oops, omega, phi I1, just like that. And that term here is exactly the denominator. So I think still on the board. Yeah. All right, we've proved that that thing up there is equal to this thing down here. Ah, wait on. What have I missed? Ah, these should be h's, right? Good, that's what we wanted to show. Right. So what we've done is taken these quantities, these endpoint dynamical correlation functions, and expressed them in terms of objects that we know how to do perturbation theory on. So we know how to do perturbation theory on these interaction picture observables. We just have this Taylor series that we worked out. We know how to do interaction perturbation theory on this S object as well. That's also, we can expand that in a series. S is none other than U, but T is plus and minus infinity. So that's the starting point for all calculations in perturbative quantum field theory. The rest of this course is, in some sense, completely automated and boring. We're going to throw in a Taylor series for S. We're going to throw in a Taylor series for phi I. We're going to have an infinite number of terms to sum, and we're going to not sum them all. We're just going to sum some of them, and then that's the end of this course. Of course, we're going to talk about Dirac fermions along the way. But apart from that, interacting quantum field theory is taking that object in the upper right-hand side and expanding it with a Taylor series and truncating that series and calculating all the terms until you explode. All right, thank you very much.